A very good morning and welcome to this course on the foundations of continuum mechanics. Today we will introduce you to strain through the finite strain tensors. So let us get started. So when discussing deformation, we develop scalar quantities, particularly measurable scalar quantities, to understand deformation. So today we'll talk about a couple of them. So the first one we talk about in terms of a measurable scalar quantity to help us understand deformation is the difference in the square of small dx squared and capital Dx squared. So let's recall what these quantities are. So we talk about an undeformed configuration and a deformed configuration, and we mentioned that we have a point P around which we are interested to quantify deformation, and then there's a point Q which we join to define the d capital X vector. Now remember, we have this Q placed in an arbitrary fashion around point P so that we can understand the kind of deformation that happens around the point P. So in the deformed configuration, we have small p and small q, which when joined gives us d small x. So what's happened here is that this d capital X vector, which is a line element in our body, it gets deformed to this d small x vector. So there is definitely some deformation happening here because we see that this vector does not look exactly the same. So what do I mean by not looking exactly the same? So we have to define some measures so that we can quantify this similarity or the lack of it. So this quantity d small x squared minus d capital X squared is just one scalar measure of this deformation. So this can be written as, in the initial notation, like this, and d small xi can be written as xi comma a times dxa, where this xi comma a is the deformation gradient tensor that we had defined in the last lecture. Right, so this d small x squared minus d capital X squared is xi comma a times dxa. That's the first dxi here, and then the other one is xi comma b dxb, and then we have dxa dxa. So I'll just move around the terms here. So I write this as xi comma a, xi comma b, dxa times dxb. Now just to make sure that we have a dxa dxb as well, we write the second term as delta ab times dxa times dxb. And this quantity here, we will call this as CAB minus delta AB. So basically, this quantity xi comma a times xi comma b is called CAB. And then we have a dxa times dxb. And further, we'll write this as the quantity twice EAB times dxa times dxb. So I'll box this and also give it a number 1. So we have defined two quantities here. So let's talk about them. The first one we defined was CAB, which we defined as xi comma a times xi comma b. And xi comma a is simply Fia, the deformation gradient tensor. So this is Fia, Fib. And if you look at this multiplication, this actually is F transpose Ai times Fib. So we can see that C is actually F transpose times F. And this quantity C is called the Green's deformation tensor. We get this by multiplying F transpose with an F. So it is obtained from the deformation gradient tensor and it's called the Green's deformation tensor. You also can see that it is symmetric. To check that, you take the transpose of C, which becomes F transpose times the transpose of F, because AB transpose is B transpose A transpose, and this becomes F transpose F again, which is C. So this implies that this is symmetric. And the other quantity we defined is this quantity EAB. So this E that we defined, or EAB tensor, has a name. It is called the Lagrangian finite strain tensor. So we defined twice of E as C minus I, or I can write that E is half of C minus I. And since C is symmetric and so is I, so this is also symmetric. Now you may wonder that we have a factor of half here. Well, this is purely for convenience that we'll see later, as this will result in some cancellation. So note that we have defined two new quantities. One is a Green's deformation tensor, and eventually the more important one is the Lagrangian finite strain tensor. Right now we only focus on the definition, and later we'll see the use of these quantities and what information they contain related to deformation. Mathematically, we see that both C, the Green's deformation tensor, and E, the Lagrangian finite strain tensor, are symmetric, and symmetricity is a beautiful property, mathematically speaking, and this will help us later. So coming back to our scalar measure, which was d small x squared minus d capital X squared, which is basically the difference between the squared of the deformed length of the line element and the undeformed size of the line element. So this was written as twice EAB times dxa dxb. I move the dxa to the left and keep dxb to the right. And from here, I can see that we have these indices which are contiguous. So this is a multiplication of a vector with this second order tensor with a dot product here and a dot product here as well. And since I had called this form, the initial form, as 1, I'll call this symbolic form that I've just written as 1a. Right, so we have defined the Lagrangian strain tensor now. So while calculating this scalar measure, we could also start in a different way, in the sense that writing everything in terms of capital X's on the right hand side, we can express things in terms of the small x's. So you notice that we have used this F inverse in this case as we had done the last time. So now everything is in terms of dxi's. In the first term, I multiply that by a delta ij to bring it to this form dxi dxj minus xa comma I times xa comma j times dxi dxj. So this simplifies to so this quantity here, we will call this small cij, and this delta minus small c, we will call this twice of small e ij, and then we have a dxi dxj. So things are very analogous to what we had done earlier, except that we have a delta minus c instead of a c minus delta, and we are using small case symbols because we are doing everything in terms of small xi's. So let's talk about this small cij. So small cij is defined as capital XA comma I times capital XA comma J, and these capital XA comma I and capital XA comma J are basically F inverse AI and F inverse AJ, which can also be written as F inverse transpose IA component and F inverse AJ. So now we can see that there's a multiplication of these two matrices. So in the symbolic notation, I can write this tensor small c as F inverse transpose dotted with and F inverse. And this small c has a name. It's called the Cauchy deformation tensor. And you can again see that this is symmetric because this is a multiplication of the quantity and its transpose. Next we come to small e, and this quantity small eij, the tensor, has a name. It's called the Eulerian finite strain tensor. And this is defined as identity minus small c times half. Again, this half is for reasons to ensure cancellation later, as we'll see. And this again is symmetric because it's a difference of identity, which is symmetric, and c, which we just showed, the Cauchy deformation tensor, is symmetric. So let's box this, and we'll call this 2. And if I write this in the symbolic notation, it's d small x squared minus d capital X squared is d small x vector dot a twice e tensor dot a d small x vector, very analogous to what we did earlier. So this we'll call 2a, and I'll box this as well. While expressing the difference d small x squared minus d capital X squared in the Lagrangian coordinates, we defined the Green's deformation tensor and the Lagrangian finite strain tensor. And while expressing things in the spatial or the Eulerian coordinates in the second case, we defined the Cauchy deformation tensor and correspondingly the Eulerian finite strain tensor. Again, we have just defined them right now. We will study them in detail later to understand the information they contain. And in case you have any confusion as to why we are doing this to identify or design tensorial quantities which help us quantify deformations. The information about deformation is contained in our chi function, that is the transformation equations or the motion equations. But we want to design these quantities so that we have readily available information about deformation contained in them, and looking at them we can understand more intuitively about what kind of deformation is happening around each and every point in the body, and basically how is the overall body going to deform from undeformed to its deformed configuration. Right, so we started the lecture by defining this measurable quantity. Let's call this A, and now we'll define another one and we'll call this B, and this scalar measure is dx1 vector dotted with d small x 2 vector. So let me tell you what they mean. So we have the undeformed and the deformed configurations, and let's say we have a point P which goes to small p as earlier, and we are interested to quantify deformation around point P or around the material particle P. So one point I take is Q, that is close to P, and this time I also take another point R which is close to P as well. And then I define these two vectors. The first one I'll call d capital X 1 vector, and the second one we'll call d capital X 2 vector. Similarly, points Q and R, let us say, go to these small q and small r. So we define these two vectors where the first one is called d small x 1 vector and second one is called d small x 2 vector. So when the deformation happens, d capital X1 line element goes to d small x1, and similarly d capital X2 line element goes to d small x2. So earlier we had taken the square of just one dx. So that told us whether the dx increased in size or not. But that did not tell us whether the dx rotated or not. So here we are getting that information whether the dx that we have is rotating or not, or in fact we see whether the angle, which let's say is theta here and theta tilde here. So what is the relationship between the angle between two line elements as the body deforms? Whether there is any shear in the body or not, or whether the angle between two line elements is changing or not. So let us do the mathematics now. So we write using the indicial notation. So this can be written in terms of the deformation gradient tensor Fi. So this becomes Fia d capital X 1a, and then the other dxi becomes Fib d capital X b2. So these are different line elements, but the quantity Fia, the deformation gradient tensor, and Fib, they are both the same tensor defined at the point P. Because we're talking about quantifying deformation at the point P. So we'll rearrange the terms. So this becomes dxa1 times F transpose AI times Fib times dxb2. And this quantity we just defined as capital CAB which is the Green's deformation tensor. And this can be written in terms of the Lagrangian finite strain tensor, which was defined as twice of E was C minus I. So C is twice of EAB plus delta AB, and then we have a dxB2. And when we expand this, this becomes dxa1 times twice EAB times dxB2 plus dxa1, and this delta AB times dxB2 becomes dxa2, and this is nothing but dxi1 and dxi2. So that's a dot between d small x1 vector and d small x2 vector. So this wheel box, and we'll call this 3. I will also express this in the symbolic notation. So this becomes the dot between d small x1 and d small x2, which is d capital X1 vector dotted with a 2e dotted with a d capital S vector 2 plus d capital X1 dotted with a d capital X2. And the symbolic form we'll call 3a. I'll box this as well. Now this number 3 equation is very important today, and we will analyze that now. So let's apply this for a situation where 1 is equal to 2. So this is a general term where d small x1 and d small x2 can be different, but it will also work if they're the same. So if 1 is equal to 2, then what we get is d small x1, and let's remove the 1 here because they're just the same. So there's only one vector d small x that we're working with, dotted with a d small x, and this is d capital X dotted with 2e dotted with same d capital X, plus now we have d capital X dotted with a d capital X. So d small x dot d small x is simply the magnitude of d small x squared, and then I moved this to the left as well. So this is d capital X squared, that equals d capital X dot 2e dot d capital X. Now isn't that the same as 1? So we conclude that equation 3 is more general, as it contains the information about 1 in it as well. So if we analyze this equation, that's good enough. We don't need to analyze the equation 1 any further. So we analyze equation 3 now. So let us start with the situation where E is 0. So let E be 0. Because we're trying to understand the impact of this quantity E that we have defined, and E is called the Lagrangian finite strain tensor. So let us see if E is 0. That is, what happens to the deformation when this strain tensor is 0. And this condition will be called no strain. Because the strain tensor is 0, so that means there is no strain in the system. So we use equation 3 with E equal to 0. So this is the equation number 3, the symbolic form. And if E is 0, then this term basically goes to 0, and we are left with dx dot dx, well, 1 and 2, is equal to d capital X1 times d capital X2. So for this case, we get d small x vector 1 dotted with d small x vector 2 is d capital X vector 1 dotted with d capital X vector 2. Now further, if we take 1 equal to 2, then what we get is that d small x squared is equal to d capital X squared, which implies d small x equals d capital X because they're both positive. They're the lengths. So let us see what we have got. So we're talking about the situation when our strain tensor is 0, the tensor that we have just defined or designed for you. And this strain tensor, if it is 0, we get a situation where d small x is d capital X. So this means that line elements do not change length when the deformation happens. So this is a kind of deformation where the length of line elements do not change. So in words, I can say that length of line elements do not change. Alright, so now let us take a situation where 1 is not equal to 2. So we are indeed talking about two vectors which are making an angle in the undeformed and the deformed configurations. So now from this equation that we had, we have d small x1 dotted with a d small x2 is d capital X1 dotted with a d capital X2. And since we just showed that for this situation where E equals 0, the length of line elements do not change. So we'll write these as d small x length 1 times d small x length 2 times cosine theta tilde. So theta tilde is the angle between these two vectors, d small x1 vector and d small x2 vector, as you can see in the figure here. So this is the angle theta between these two line elements, and the line elements deform to these small dx1 and dx2, and the angle between them changes to theta tilde. So theta tilde is the angle between d small x1 and d small x2, and theta is the angle between d capital X1 and capital X2. So this becomes equal to d capital X length 1 d capital X length 2 times cos theta. And since for the case when E equals 0, we have this as d capital X1 and this is d capital X2. Which basically becomes cos theta tilde equals cos theta. Now theta is a positive angle, so we can write theta tilde equals theta. So in words I can say, so let us summarize the situation. So all lengths stay same and all angles between elements stay same. So this implies that we're talking about a rigid body rotation. That's what happens in a rigid body rotation, that all lengths stay same and the angle between two line elements also stay the same. The body as a whole will rotate, but the angle between two elements originating from a point P will stay the same. So the result that we have got is actually quite interesting. So the quantity E that we just saw, which is our first strain tensor, the Lagrangian strain tensor in this case, it is designed to measure deformation, not rigid rotations. So remember our F tensor, which was the deformation gradient tensor, there by definition we had removed translation. So what was left was rigid rotations and deformations. So here further what we have done is by defining this new tensor E, we have even removed rotations from the quantity. So this deformation we are talking about can be a stretching because E has information about change in length as we just saw, and also shearing. So shearing is when the angle between elements change, and stretching is when their length change. So strains in general will be defined just one. There are others as well. They measured the deformation of elements. That is what the quantity strain is for. So pictorially, I can say that if we have an element that looks like this, it's a square element. It may get stretched, so it may become larger in size, although the stretching can be different in different directions. And it can also change its shape, that is shearing, that is the angle changes. But this element becoming this, which basically is rotation, this information is not contained in the tensor E. So we showed that E equal to 0 is a pure rotation. We can show the other way around, that if there's a pure rotation happening as a deformation, that means that the quantity E by its definition is 0. So let's do that. So we define motion as this chi function like this, which in the vector form can be written as small xi is some small xi function of capital X. Now when we have a pure rotation happening, then we know that this is equal to AIB capital XB, because remember we had shown that the chi function is nothing but a linear transformation. So our small x1, small x2, small x3 was written as a transformation vector times capital X1, capital X2 and capital X3. And since we're talking about a pure rotation, that means this is our tensor R, which is a rotation tensor. And we have discussed rotation transformations when we discussed about the tensor transformation properties. So this is something which we called the matrix A earlier. That's the reason I've written an A. So A corresponds to a rotation. So rotation of a vector in a transformation or deformation is basically as if your coordinate system has rotated. So this matrix here is an orthogonal matrix as it corresponds to a rotation. Now, of course, we can have other kinds of transformations as well. They'll all be linear, but they'll be of different types. But this is a special case that we are taking, and that corresponds to rigid body rotation. So if this is how the chi function is defined, now we can calculate our deformation gradient tensor Fia, which was defined as xi comma a. So this xi is given as aib xb. So this becomes, now aib is just some matrix. So this is capital XB comma a. And this capital XB comma a is simply delta BA. So this becomes A I A. So this is our FIA. And how did we define our Lagrangian finite strain tensor? That was half of F transpose F minus an identity. So this becomes half of A transpose A minus identity, because our F is the same as the transformation matrix A here, and A is orthogonal because it's a rotation transform. So that means this quantity is an identity. So this becomes half of I minus I, which is a 0. That is exactly what we had to show. That if there's a pure rotation happening from the undeformed to deformed configuration, the body rotates purely, then that means that the Lagrangian finite strain tensor is 0. And we have shown that. So the quantity E is a 0 for pure rotation. Till now, we have expressed our Lagrangian finite strain tensor in terms of F tensor, which basically is saying that we have expressed this in terms of our chi function. But many a times we want to express this in terms of the displacement field. So particularly, we write E as half of F transpose F minus I, and in the initial notation this is EAB is half of, now F transpose F is xi comma A times xi comma B minus delta AB. So we would want to write these terms in terms of the displacement field UI. So let us do that. Now we defined the displacement as small xi minus capital Xi. So we can write small xi as ui plus capital Xi, and this means that small xi comma a becomes ui comma a plus xi comma a, and this simply is delta ia, because xi comma a is del capital Xi by del capital Xa. So we will substitute this and get the expression for EAB. So we can see that this cancels, and twice EAB can be written as UA comma B plus UB comma A plus the product term, which is UI comma A times UI comma B. So we'll box this, as this will be an important result which we'll be using later for defining a linearized strain tensor. So these are displacement gradients and not deformation gradients. So we have expressed the Lagrangian finite strain tensor in terms of displacement gradients. Now we've been talking about the Lagrangian finite strain tensor, but similarly we can also express the Eulerian finite strain tensor, which was EIJ, in terms of the displacement gradient tensors. So this is how we have defined the Eulerian finite strain tensor. So we can write our displacement field as small x minus capital X, and since we are interested to write capital X derivatives with respect to the small x's, so we'll have to define the displacement field in the material coordinate system. So this becomes xa minus capital Xa, and now I can write capital Xa as small xa minus UA, which when differentiated with respect to small I becomes small x a comma I minus UA comma I. And this again is a delta AI. So this becomes a delta AI minus UA comma I. So we'll substitute that here. So the first capital X a comma I becomes this, and the second capital X a comma j becomes this. Let us expand this. So these cancel, and we have twice small eij, that is the Eulerian finite strain tensor, and that's equal to ui comma j plus uj comma I minus ua comma I times ua comma j. And we will box this as well, because this is going to be an important quantity for continuing the discussion next time. So this is the expression for the Eulerian finite strain tensor in terms of the displacement gradient tensor. So today what we did was that we defined the finite strain tensors as promised. For that we started with intuitive scalar measures. Number A, which is d small x squared minus d capital X squared, that is the difference in the square of the length between undeformed and deformed configurations for elements. And then we took the change in angles. And from there, we found out the expressions in terms of the Lagrangian finite strain tensor. Although we could have done the analysis using the Eulerian finite strain tensor as well, we just chose one approach over the other. And this approach was more comfortable to understand because it tells us how the elements in the material configuration are changing in the spatial configuration. Going back is a little less intuitive. And then we understood the meaning of strain, that when the strain is 0, we get pure rotations. So it is this strain tensor E that has all the information about the body stretching, which could be different in different directions, but it's a pure stretch, and shearing, which is the angle between elements changing. And this is the kind of deformation that we are interested particularly in the course of continuum mechanics. So you see that we are isolating the effects of deformation through these strain tensors. So what's important as a takeaway from today's lecture is for you to understand the definition of these quantities, particularly the strain tensors, the Lagrangian and the Eulerian strain tensors, and we'll be solving problems in the tutorial where we'll ask you to calculate these and further analyze these geometrically. And when we look at geometrical picture, that is when we try to visualize how a square element deforms into a rhombus element, for example, and we look at its corresponding Lagrangian finite strain tensor, we will understand what is the meaning of the terms in this tensor. But as I said, that is only possible through exercises that we'll be doing later, because the lectures are quite heavy in terms of the derivations this week. But these derivations are important. We need to understand the meaning of these terms. So this expression that we have gotten for the Eulerian finite strain tensor has a product of a displacement gradient with itself. Now this creates something called a nonlinearity, which we as engineers do not like. So in the next lecture, we will try to linearize this so that we can understand the strain tensor in a more intuitive fashion, as we humans tend to understand linearities more easily than nonlinearities. But of course, these linearities are done under special situations, and we'll discuss those special infinitesimal deformations in the next lecture. So thank you very much, and I'll see you next.